3D printer. It's made by with electrobeam melting method. You can melt slices of titanium powder. That is slice by slice. You can build in such a way any geometry. So with this technology we have developed a lot of structure, very porous structure, to rebuild and to regenerate bone.
Okay.
Our knowledge is based on regeneration of big defects of bones. We made several tests with animals with high porous structure, porous up to 90%. Part of the volume, the 90%, is vascularized. Vessels go inside and then start to grow up and to rebuild your bone, your own bone. The big advantage is that there is, with this technology and with this new philosophy of design and manufacture implants for bone replacement, is that you should use only one implant one time. I mean, you don't need to replace implants.
So it's forever.
Actually, yes. You put and then the final result is a mix between your new bone reconstruction and a scaffold that is your implant. So when it's everybody together, then can stay there because it's your own bone. 90% of this volume is your own bone. Another very important application. In the chest, the needs are different than in normal bones, in the loading bone. In the chest, what you need is to have the possibility to expand
to be flexible, right?
And flexible. So it's not important to regenerate, but to follow the respiration movement during brace. So this is a patent. This structure are patented by us. This is one implant for a case that we are doing in Germany, and it's a reconstruction on the second, third, fourth ribs, and it's you can see that it's totally elastic and it's fixed. This is a reconstruction for big tumors. This was a basocellular tumor that was in a big area. This structure is our structure, and we were the first in the world to develop elastic implants to follow the braiding movement. We make one implant, one patient. This is for one patient. We receive the tomography, the computer tomography. We rebuild the model in 3D. And we can work on the CAD, in the computerized design, and then we work designing directly on the reconstruction of the tomography. It's working, not only working, I mean, the patients can restart breathing without any problem of respiration. Normally, what is in the market now is rigid. So you can reconstruct. There is one part of the needs of the reconstruction that is good. That is the protection part. If it's rigid, it works. But then you can lose up to 20% of the capacity of the volume of the respiration volume. Patients that were treated with the normal rigid implants, normally after the reconstruction, they can breathe not in a physiological way. They lose capacity, so if they climb stairs or if they have to make some activity sports, they can't breathe so well as a patient that you can restore the total physiological capacity of the lungs. This is a custom made in Germany that will implant in a patient in the next 20 days.
Wow. And where?
And in Germany. In an hospital of the middle Germany. This part we need to rebuild bone. So this is like it looks reconstruction for bone regeneration. It's porous inside, and there is a shell that is with the same pore in the direction of the inside network. The clavicle is a challenger. Still a challenger because it's a joint that it works in an opposite direction. Normal joint works in compression. The concave part in contact with the convex one with the compression, it will fit always, and it works. But clavicle works in destruction. The part that can join in the normal working of a clavicle are soft tissue around that prevent luxation. We are mimicking the same principle than nature. I mean, we have an artificial ligament that works like surrounding soft tissue and avoid that the joint can be luxated.